phase contrast microscopy is an optical microscopy technique that converts phase shifts in light passing through a transparent specimen to brightness changes in the image. Phase shifts themselves are invisible, but become visible when shown as brightness variations. When light waves travel through a medium other than vacuum, interaction with the medium causes the wave amplitude and phase to change in a manner dependent on properties of the medium. Changes in amplitude arise from the scattering and absorption of light, which is often wavelength dependent and may give rise to colors. Photographic equipment and the human eye are only sensitive to amplitude variations. Without special arrangements, phase changes are therefore invisible. Yet, phase changes often carry important information. Phase contrast microscopy is particularly important in biology. It reveals many cellular structures that are not visible with a simpler bright field microscope, as exemplified in Figure 1. These structures were made visible to earlier microscopists by staining, but this required additional preparation and killed the cells. The phase contrast microscope made it possible for biologists to study living cells and how they proliferate through cell division. After its invention in the early 1930s, phase contrast microscopy proved to be such an advancement in microscopy, that its inventor Fritz Zernike was awarded the Nobel Prize in 1953. Working principle. The basic principle to make phase changes visible in phase contrast microscopy is to separate the illuminating background light from the specimen's scattered light, which make up the foreground details, and to manipulate these differently. The ring-shaped illuminating light that passes the condenser annulus is focused on the specimen by the condenser. Some of the illuminating light is scattered by the specimen. The remaining light is unaffected by the specimen and forms the background light. When observing an unstained biological specimen, the scattered light is weak and typically phase-shifted by -90° relative to the background light. This leads to the foreground and background having nearly the same intensity, resulting in a low image contrast. In a phase contrast microscope, the image contrast is improved in two steps. The background light is phase-shifted -90° by passing it through a phase shift ring. This eliminates the phase difference between the background and the scattered light, leading to an increased intensity difference between foreground and background. To further increase contrast, the background is dimmed by a gray filter ring. Some of the scattered light will be phase-shifted and dimmed by the rings. However, the background light is affected to a much greater extent, which creates the phase contrast effect. The above describes negative phase contrast. In its positive form, the background light is instead phase-shifted by +90°. The background light will thus be 180° out of phase relative to the scattered light. This results in that the scattered light will be subtracted from the background light to form an image where the foreground is darker than the background, as shown in Figure 1. Related methods. The success of the phase contrast microscope has led to a number of subsequent phase imaging methods. In 1952 Georges Nomalsky patented what is today known as differential interference contrast microscopy. It enhances contrast by creating artificial shadows, as if the object is illuminated from the side. But, to achieve this DIC microscopy uses polarized light, making it unsuitable when the object or its container alter polarization. With the growing use of polarizing plastic containers in cell biology, DIC microscopy is increasingly replaced by Hoffman modulation contrast microscopy, invented by Robert Hoffman in 1975. Traditional phase contrast methods enhance contrast optically, blending brightness and phase information in single image. Since the introduction of the digital camera in the mid-1990s, several new digital phase imaging methods have been developed, collectively known as quantitative phase contrast microscopy. These methods digitally create two separate images, an ordinary bright field image and a so-called phase shift image. In each image point, the phase shift image displays the quantified phase shift induced by the object, which is proportional to the optical thickness of the object. See also, live cell imaging, phase contrast imaging, phase contrast X-ray imaging. References. External links: Optical microscopy primary Europhase contrast microscopy by Florida State University.